Welcome back to Cosmic Lens. Sit back, relax, and enjoy the show. In the silent emptiness of space, a star dies. One moment it shines as a distant pinprick in the darkness. The next it erupts in a soundless flash of light that briefly outshines an entire galaxy. A titanic explosion unfurls in utter silence. No roar, no crash, for in the vacuum of space there is no medium for sound. It is a cosmic firestorm, seen across light years, a brilliant beacon of death that appears without warning and vanishes just as quickly. For a few fleeting weeks, this single dying star pours out more light than billions of suns, blazing so brightly that if we were watching from a nearby world, it would paint shadows on the ground and outshine the night's full moon. Yet there is only silence. The star's final scream is in light, not sound, an immense outpouring of energy racing outward through the dark, telling anyone who cares to look that a star's long life has ended in cataclysm. What are we to feel witnessing such a violent cosmic death? There is terror in the idea. A star, an object of almost eternal constancy in our sky, can explode without mercy. But there is also awe in that silent explosion. We sense power beyond comprehension, the death throes of a sun many times larger than our own, unleashing energy in a few seconds that our sun will not emit in 10 billion years. Here is a celestial paradox, an event at once beautiful and destructive. A supernova, as astronomers call it, is the most brilliant of stellar fireworks, a soundless eruption of light so powerful it can be seen across the universe. It is nature's way of shouting across the cosmos, a final cry of a dying star that echoes in starlight rather than sound. We watch in reverence, hearts humbled, for this silent stellar eruption is more than just an ending. It is a moment of cosmic rebirth, a paradoxical creation forged by destruction. The universe, we will find, is full of such paradoxes. But how can a star, a colossal ball of plasma that has shone for millions of years, simply explode? What chain of events leads to this soundless flash in the sky? To answer these questions, we must journey into the heart of that star, into the forces and fires that sustain it, and ultimately into the tragedy that ends its life. Only then can we understand why this cosmic violence is not an empty tragedy, but a necessary drama that creates new worlds and even life. So let us venture now into the story of a star's life and death, a story written in the language of astrophysics and nuclear fire, yet rich with poetic grandeur, the story of a supernova. Imagine a star many times more massive than the sun, born in a nebula of gas and dust. For eons it has burned brightly, converting simple elements into heavier ones in a relentless alchemy. In its core, hydrogen, the simplest of all elements, fuses into helium, releasing the energy that makes the star shine. This process of fusion is the star's lifeblood, a delicate balance between pressure and gravity. Deep in the core, the outward push from fusion-generated heat fights against the inward crush of gravity. As long as there is fuel to burn, the star maintains this equilibrium, shining steadily in the firmament. But stars, like living things, have cycles. Our massive star eventually exhausts the hydrogen in its core. After millions of years of brilliant stability, gravity, ever patient, begins to gain the upper hand. The core contracts and heats up until a new fusion fire ignites. Now helium fuses into carbon and oxygen. The star has entered old age, swelling into a bloated giant. If we could see it up close, we would find its appearance transformed, often into a red supergiant, a star swollen to hundreds of times its original size. Its outer layers cooled and ruddy. Inside, however, the core burns hotter and hotter as it fuses heavier elements in turn. Shells of fusion surround the core like the layers of an onion, each shell burning a different element. Closest to the center, carbon fuses into neon. In a shell above, neon burns to magnesium and oxygen. Above that, oxygen fuses into silicon. Each stage produces the fuel for the next, and each stage of fusion burns faster than the last. What once took millions of years burning hydrogen gives way to shorter phases. Helium burning lasts a fraction of that time, carbon burning perhaps only centuries, oxygen mere months, and finally, silicon burning might last only days. The star is living on borrowed time, rushing through its life's finale at breakneck speed. Layer by layer, like a great cosmic onion, the star builds up a core of iron deep in its center. Iron. This is a fateful element in the life of a massive star. For all the previous fusible fuels, hydrogen into helium, helium into carbon, and so on, fusion released energy. This energy held up the star's weight, staving off gravity, but when fusion creates iron, the game changes. Fusing iron does not release energy, it consumes it. The atomic nucleus of iron is the most tightly bound of all common elements. You cannot fuse iron into something heavier without paying an energy price, and so as iron accumulates in the core, the star is unknowingly building a bomb at its center, a gravitational time bomb. With no more energy to be gained from fusion, there is no outward pressure that can be won from turning iron into heavier elements. The stellar core, once a powerhouse of light, becomes a dead weight of iron atoms. In the star's final moments, the iron core grows to a critical mass. Imagine a sphere of iron as large as Earth, but containing nearly the mass of our Sun, buried at the center of a star, hundreds of millions of kilometers across. This core is supported only by the desperate pressure of electrons jostling in the iron nuclei, a quantum pressure holding collapse at bay, like an overloaded spring. But as the iron core's mass approaches a limit, even this exotic electron pressure cannot hold back gravity. The core has run out of road. In a fraction of a second, it collapses. Gravity slams the core inward with incredible force, and nothing in nature can stop it. At the center of the star, densities and temperatures spike to billions of degrees. Iron nuclei disintegrate. High-energy photons smash iron atoms into fragments of helium, protons, and neutrons in a process called photodisintegration. Electrons are forced into protons, turning them into neutrons and releasing a flood of neutrinos. The core, in effect, is utterly breaking down, and in the span of a heartbeat, it implodes from a sphere the size of a city to an ultra-dense ball of neutrons, only a few kilometers across. Gravity has won. The core is now a neutron star, an object so dense that 1 teaspoon of its material would weigh billions of tons on Earth. If the star is extremely massive, the collapse may not stop even there. It can continue into an infinite decimal point, a newborn black hole. For an outside observer, this moment is invisible. It happens hidden in the star's interior, but its consequences are about to burst forth. As the core collapses, it reaches fantastical densities, even comparable to an atomic nucleus. At that point, the collapse rebounds. The core's inner region stiffens abruptly, and the infalling material crashes against this hard stop. The result is a shock wave that begins to travel outward. Think of it like a sudden jolt. The core, having imploded, bounces slightly and sends a powerful pressure wave racing up through the star's layers. Yet even this might not be enough to blow the star apart. The shock wave expends tremendous energy, ripping apart iron nuclei in its path, and it can stall within the star as it encounters the overlying heavy layers. Here, the ghostly heroes of our story emerge: neutrinos. These nearly massless, elusive particles were released in staggering numbers during core collapse. A flood of them pours out of the core, carrying away the energy of gravity's triumph. In fact, 99% of the energy of the collapse is released as neutrinos, an almost inconceivable torrent of invisible particles. Under normal circumstances, neutrinos hardly interact with matter at all, but the sheer intensity of the neutrino blast from the collapsing core is unprecedented. In that brief moment, the core shines with neutrinos more powerfully than a billion suns shine with light. As the shockwave stalls, These neutrinos streaming outward deposit a fraction of their energy into the star's layers, rejuvenating the shock. It's as if an army of ghosts all struck in unison, delivering a final push to blow the star apart. A deafening, silent roar in neutrinos propels the shockwave outward again. Within milliseconds, the core has transformed from a quiet iron ball into an engine firing out neutrinos and launching a shock front through the star. Now the doomed star's outer layers finally feel the effects. A ferocious blast wave races outward from the core, plowing through each overlying shell of elements. The star's immense envelope, hydrogen, helium, carbon, oxygen, all the layered elements built up over its life, is violently ejected. The shock heats the stellar material to incandescent temperatures, so as it blows out to space, it begins to glow brilliantly. The star is literally tearing itself apart from the inside. Within hours, the shock reaches the star's surface. The once stable star has become an expanding fireball. To any distant onlooker, this is the moment the star suddenly brightens by orders of magnitude, announcing the supernova. The dying star, which may have been a modest point of light before, now becomes something like a miniature galaxy in appearance, a single point shining with the luminosity of billions of suns. For a brief time, this one star's explosion can rival the brightness of an entire Milky Way of stars. Imagine it, a pinpoint of light in the sky, outshining every other star in its galaxy, pouring out energy at an impossible rate. In one supernova, more energy can be released than our sun will radiate over its entire 10 billion year lifetime. The numbers defy imagination. The exploding star's luminosity can reach tens of billions of times the sun's output. Seen from a nearby planet, the night would turn into day. For weeks, even from thousands of light years away, such a supernova might be visible with the naked eye, as has happened at a few points in human history, when supernovae in our galactic neighborhood briefly appeared as new stars in the sky. The Chinese, over 2 millennia ago, recorded a mysterious guest star that shone for months, where no star had been before. Medieval astronomers, too, were astonished by sudden stars that could even be seen in daylight. All of these were supernovae, the spectacular deaths of distant suns flaring into visibility across the void. In these moments of peak brilliance, the supernova is a mesmerizing sight. The star's outer layers hurtle into space at thousands of kilometers per second, a spherical tsunami of gas racing outward. The material glows from the immense heat of the explosion, producing an expanding shell of radiance. If the star was a red supergiant before it exploded, the shock may take some time to break out, and the supernova's light will then linger with a gradual decay, sometimes showing a plateau of brightness as its expanding hydrogen-rich envelope shines. If the star was a blue supergiant, more compact and hotter, the explosion might rise and fall faster, perhaps with an initial burst of high-energy radiation. Different stars produce different light curves in their death. Some supernovae maintain peak brightness for weeks, whereas others fade more quickly. In all cases, however, the spectacle eventually wanes. The enormous blast, having expended its energy, sees its debris cloud expand, thin out, and cool over months. The supernova's visible light diminishes, often transitioning to a dim nebula of glowing embers. But in those first days and weeks, the radiance is unrivaled. The supernova floods the spectrum with light, from energetic X-rays and ultraviolet flashes generated at shock breakout to the optical light that we see with our eyes and onto infrared and radio waves. As the ejector plows into surrounding space, it is a multi-wavelength beacon, proclaiming a star's demise. Not every star ends this way. Only those of sufficient mass die in such spectacular fashion. Stars born with more than about 8 times the sun's mass are destined for these core collapse supernovae. Our sun, by contrast, will never explode. Far in the future, it will swell into a red giant and then gently shed its outer layers to form a planetary nebula, leaving behind a dense ember called a white dwarf. But massive stars live fast and die young. They burn through their fuel quickly and then explode, as we have seen. The supernova we've described, the collapse of a massive star's iron core, is one major type of stellar death. Yet intriguingly, there is another very different way to trigger a supernova. Not all stellar explosions come from a single massive star collapsing. Some come from a more subtle kind of stellar doomsday, a runaway nuclear detonation on a white dwarf star. In binary star systems, two stars orbiting each other, it sometimes happens that one star is a white dwarf, the tiny dense remnant of a sun-like star, and it begins stealing matter from its companion. If the white dwarf gains enough mass, it can reach a critical threshold at which the pressure and temperature in its core ignite a furious wave of nuclear fusion in a matter of seconds. Carbon and oxygen inside the white dwarf detonate in a thermonuclear blaze. The white dwarf is blown to bits in a special kind of supernova explosion. Astronomers call a Type Ia supernova a thermonuclear supernova, and it differs from the core collapse supernova of a massive star. Such stories may seem far from scientific truth, yet they reveal something fundamental about us. We have always been storytellers, trying to shrink the darkness between distant points of light into something we can cross. The dream of instantaneous travel, of portals and shortcuts, is a recurring theme. We whispered it in our fables and wrote it into our fiction. As soon as we had the language of science, when technology advanced, and we began to grasp the true scale of space, as we venture through the mind-bending possibilities of wormholes, parallel universes, and the mysteries of space-time, we are reminded of how much we have yet to discover. The very idea that wormholes could connect different realms, be they alternate realities, separate universes, or distant parts of our own, stirs a sense of wonder and curiosity. These theoretical passages challenge our understanding of reality itself, urging us to imagine a cosmos far more complex and interconnected than we've ever known. Though wormholes remain speculative, they continue to inspire both scientific exploration and the human imagination. Whether they exist as natural cosmic structures or potential technological marvels, the dream of traveling beyond the bounds of our universe beckons. As our tools and knowledge advance, we may one day uncover the hidden pathways through the fabric of space-time. Until then, we can only marvel at the questions they raise and the limitless horizons they open in our search for understanding. In the end, the exploration of wormholes isn't just about navigating the universe, it's about pushing the boundaries of our own imagination, redefining the very essence of existence, and perhaps, in some distant future, bridging the gap between the stars, the minds, and the infinite possibilities that await us. The journey has only just begun. Physicists have poured a lot of thought into whether these paradoxical situations could actually happen. Some have concluded that any attempt to create a time loop with a wormhole would result in conditions that destroy the wormhole or otherwise prevent the paradox. Even a theoretically stable wormhole might not be eternal. Maybe it slowly leaks its exotic matter, or quantum effects cause the exotic state to degrade over a long time. Millions of years, a wormhole could gradually contract or pinch off if not maintained. If civilizations rely on wormholes, they'd have to monitor their health, a kind of infrastructure maintenance. Imagine a far future scenario where a forgotten wormhole network starts collapsing because the generators keeping them open fail. Star systems could become isolated again, or travelers could be lost mid-route. Given all these hazards, any journey through a wormhole would be taken with great caution. It would be like crossing a bridge made of glass over a chasm, hoping it doesn't crack under your weight. One would likely send probes first, measure conditions, possibly actively stabilize the wormhole with some engineered device, like feedback systems, injecting bursts of negative energy, or adjusting the throat geometry on the fly to counteract perturbations. Perhaps using a wormhole will always remain a delicate operation, not a casual stroll. On the flip side, understanding these challenges is useful. Each of them suggests a way to test or constrain wormholes' existence. For instance, If wormholes tended to collapse with too much mass, maybe none above a certain size could survive, which might tell us why we don't easily see them. Or if they radiate, maybe we could detect an unusual radiation spectrum from what looks like an isolated black hole. So far, we have no direct evidence that any of these speculated issues have manifested in reality. But then we haven't found a wormhole either. It might be that if nature allows wormholes at all, they exist only in realms we haven't observed, like at Planck scales or in extreme conditions, or are carefully hidden by cosmic censorship of a sort. The bottom line, traversable wormholes would be high-maintenance, temperamental beasts. They're the divas of theoretical physics, requiring special conditions, throwing fits if stressed, and possibly self-destructive if you break their rules. But if one could tame such a beast, the rewards are immense. Knowing these caveats, we can now turn our attention to the practical side of things. How might we detect a wormhole if one exists out there in space? After all, it's one thing to theorize and simulate on a quantum computer, but finding a real wormhole would shake the foundations of science. There's also the question of security and misuse. A wormhole can be a doorway for commerce and travel, but also potentially a conduit for invasion or catastrophe. An enemy could send troops or weapons through a wormhole, bypassing all traditional defenses. Even a small wormhole could be used maliciously. Imagine someone opening a tiny wormhole in the middle of a city and funneling dangerous substances or deadly radiation through it from a safe distance. On a cosmic scale, one could theoretically divert matter from a star, like a stream of plasma, through a wormhole to threaten another world. Such scenarios mean that if wormholes exist, there may need to be agreements or technologies in place to police their usage, much like nuclear materials are monitored today. Wormhole time travel capability complicates ethics even further. If a wormhole network allows forward and backward time jumps by virtue of relativistic transport of one mouth, how do we handle the possibility of altering history? It might become necessary to establish strict laws, e.g., a prohibition on turning a wormhole into a time machine, perhaps enforced by international accord or automatic fail-safes in wormhole generators. One could imagine a chronology protection agency, a nod to Hawking's chronology protection conjecture, either a literal task force or simply the collective agreement of scientists to avoid creating causality paradoxes. People could be tempted to use wormholes to go back and prevent tragedies or gain advantage. Lottery numbers, anyone? This raises moral dilemmas. Do we allow controlled, consensual changes to history, or is any change a violation of the rights of those who lived through the original timeline? Most thinkers suspect that unrestricted time travel would be destabilizing. Thus, ethically, it might be near universally outlawed, even if physically achievable. Beyond overt misuse, there's the matter of equity. If wormholes are expensive or hard to make, initially only a rich elite or powerful governments might have access, widening the gap between those who can cross the stars and those who cannot. There will be ethical pressure to democratize such technology, to avoid a universe where a few get to gallivant across space-time while others are stuck on their home worlds. History has shown that with airplanes, telephones, and the internet, widespread access eventually became key to unlocking the full benefit of the technology. Perhaps wormholes would follow a similar path, from military or elite use to general public utility. Still, ensuring fair access would be a challenge, requiring conscious effort. Finally, consider the environmental and existential risks. Every wormhole manipulation is an interference with space-time structure. Could creating or using wormholes have unforeseen side effects, like triggering that vacuum decay scenario or disrupting orbits? Ethically, we'd need to weigh the potential harm of tearing space-time against the benefits. It might be akin to early atomic scientists worrying about setting the atmosphere on fire with a nuclear test, an extremely low probability event, but with annihilating consequences if it came true. Responsible science demands we assess these risks honestly. Perhaps initial wormhole experiments would be done far from Earth in case something went awry, or on a small scale before scaling up. In summary, Wormholes would demand a new ethical framework. We'd need a blend of caution, international cooperation, and forward-thinking regulation to use them wisely, much as the world came together, however imperfectly, to prevent nuclear war and to manage space resources peacefully. A similar or greater unity might be required to handle wormhole technology. The goal would be to maximize the wondrous benefits: quick travel, instantaneous communication, cultural exchange, while minimizing opportunities for disaster or domination. Achieving that balance could be one of humanity's greatest ethical tests, essentially asking, can we wield the power of the gods without succumbing to our very human flaws? Handled wisely, wormholes might even open pathways to domains utterly foreign to us. Among the wildest possibilities is the idea of connecting not just different regions of our universe, but entirely different universes across the multiverse, bridges to parallel realities.